digital twins are going to be a theme for this session so far, because I'll talk about them as well. But I first want to start with this picture. I love this picture of the Earth at night from space. I like to show it at international conferences because everyone in this room comes from somewhere on this picture. And as seen the bright points of light spanning the globe, we can see that cities are a big part of modern civilization. And our cities can be both a way for progress, but also a way for degradation. Cities are our greatest engines of economic growth, resource efficiency, artistic creativity, cultural development, even though they occupy less than 2% of the earth. But they're also our greatest concentrators of consumption, pollution, waste, and inequality. And they consume more than 75% of resources and are responsible for more than 70% of global CO2 emissions. This morning we heard a lot about the problems that cities can have, and also the opportunities that they present. And which kind of cities we want, the good or the bad, whether they're in line with sustainable development goals, that's the challenge we've come here to discuss today. But actually I want to talk about a new type of framework. And in doing so, I hope this leads to a new way for us to think about these challenges in all of our cities, particularly smart cities, and to solve our common problems in new and exciting ways. And the framework I propose is called the Urban Wealth Quality of Life Challenge. So let's start with an urban GDP per capita on the x-axis, from low to high. And on the left axis, let's measure the potential of a singularly designed urban system to improve quality of life. In urban areas with a low GDP per capita, the introduction of a standalone, singularly designed wastewater treatment system, in this case an anaerobic digester studied by one of my PhD students in Zambia, can result in very big improvements in quality of life. That single system made the surrounding community and its residents much better off. But in urban areas with a high GDP per capita, another standalone, singularly designed system, maybe a new nanoparticle filter for a wastewater treatment plant, it just doesn't make life that much better. For the residents of San Francisco, they don't notice installing that nanofilter into the wastewater treatment plant. It may be highly efficient and the source of wonderful academic publications, but no one cares. Thus, as urban GDP per capita increases, the potential of standalone systems to improve urban quality of life decreases. So let's put another axis. Let's look at the potential of a holistically designed urban system to improve quality of life. In this case, let's look at Disney's new industrial ecology approach at their Shanghai resort that takes in natural gas, cardboard, vegetation waste, food scraps, grime, gray water from resort hotels, contaminated wastewater, and excess heat from CCHP, and produces potable water, hydrogen gas, oxygen gas, nitrogen fertilizer, high purity lignin, and ethanol. For an urban community, the simultaneous provision of electricity, cheap heat, drinkable water, waste handling, free natural fertilizer, combustible fuels, and valuable chemical feedstocks is a positive change. However, for a city with a low GDP per capita, it's uncertain whether such a system would be a benefit or a white elephant. Thus, as GDP per capita increases, the potential of holistically designed integrated systems or smart cities to improve urban quality of life increases. The question we have to ask, as expressed here, one of our challenges is that we're only good at designing, implementing, operating, financing, and using the standalone type of systems. As a civil engineer, I am most guilty of working in these kinds of silos. Real integration across physical systems, technology systems, social systems, financial systems, and governance systems is really hard. But the challenge posed is getting wealthy countries to move up this axis and developing countries to make the leap at the right time. But how do we do this? Well, my colleagues and I at Stanford have thought about a new type of infrastructure, and we call it metastructure. This is something that was alluded to earlier today as invisible infrastructure with blah blah. So let's talk about a big Silicon Valley company, Uber. they definitely added to the transportation capacity of the San Francisco Bay Area and many other cities around the world. But they didn't do this by building a light rail system, building any lanes of roads, or even buying a single car. By using some new technologies and some old technologies, and most importantly, an innovative business model, they brought an existing set of assets together in a new and innovative way to increase the supply of transportation. While acknowledging there are many downsides to the Uber business model and the effects that it can have on the urban community, it's an example of what we call metastructure. So let's talk about another Silicon Valley company, Kickstarter. By linking together like-minded individuals passionate from the project, Kickstarter has expanded the supply of capital for important efforts. In the context of infrastructure, more than 1,200 crowdfunding campaigns have been launched since 2010, raising over $10.5 million. The campaigns have funded public parks in New York, bicycle sharing programs in Missouri, and the construction of bike lanes in Colorado. Once again, using some new technologies and some old ideas and an innovative business model, Kickstarter brought together an existing set of assets in a new and innovative way to increase the supply of infrastructure lending. Once again, metastructure. More formally, we view the urban metastructure as a set of physical infrastructures, digital IT technologies, regulations, and policies equally important. Financing, community engagement, stakeholder management, businesses and business models, partnerships, and other institutions that have to be created, applied, and sustained in concert with one another to provide a high quality of life in urban areas and future cities. And if you don't like Uber and Kickstarter, we talked about Airbnb, BlaBlaCar, and many others earlier today. These are just a few examples of what we call this metastructure. And the use of a new word that is not infrastructure is important, because this is not what we would typically call infrastructure. It is above infrastructure. It arches over it. It's metastructure. So as we think about a strategy for studying, planning, building, and living in these deeply integrated urban systems, we have to layer the metastructure upon one another. And that can be components like integrated urban material flows, infrastructure IoT performance sensing and adaptation, integrated wastewater treatment and energy production, digital twinning and optimization of urban operations, new governance for urban systems and finance models, and innovative urban business models and companies. This is what we call Industry 4.0, as we start to layer all of this metastructure on top of itself. And so this layer metastructure must also address both parts of the challenge. Thus, we must ask, how do we retrofit existing and wealthy cities like Seoul, Copenhagen, San Francisco, and Beijing with the metastructure necessary to thrive over the coming century? And how do we equip cities, new cities, and those yet to be built with the metastructure to support an ever-growing, more sophisticated population? So today, I want to focus the rest of my talk on a cyber-physical financial infrastructure system and its nexus. So we'll talk about some new financing for smart cities, digital twinning, one of my favorite topics, and then some conclusions. There's a tremendous need for infrastructure funding worldwide. It's been estimated that through 2030, somewhere between $57 and $67 trillion of investment will be needed globally, 75% of it in cities. In the U.S. alone, that's $3.6 trillion in the next 5 years. Deferred maintenance will make a large part of this investment, while at the same time funding responsibility is shifting from national to local governments in many countries. The irony is that there's plenty of money to support these projects. In fact, there's too much money around the globe chasing too few what we call bankable projects, those of a high enough quality for investment. Institutional investors are allocating more money and getting smarter and looking to use new financial innovations to engage in privatization of greenfield, brownfield, and what we call olive infrastructure assets. Traditionally, paying for infrastructure has involved a basic set of economics. First of all, there are grants and subsidies that are provided by multilateral development banks or intergovernmental transfers from national and regional governments to municipalities. Local taxes have also long been used to include property taxes, sales taxes, and income taxes. Historically, funding has also come from tolls, motor fuel taxes, and user fees. More recently, more innovative funding models like tax increment financing have been introduced to capture part of the increase in property values stemming from infrastructure investment. However, none of these traditional models leverage smart cities. So in order to leverage smart system innovations, I'd like to break them down into three interconnected sets. The first set deals with new ways of collecting and classifying information, and includes ubiquitous sensing networks and a broader set of performance measures that redefine how we measure and define performance. The second set of innovations deals with new modeling and analysis capabilities and includes high-fidelity physical models of urban systems and an ever-expanding data storage and cloud-based analytics capacity. And the third set of innovations deals with new decision-making schemes that leverage advanced digital knowledge management tools and new municipal governance and finance models. We're interconnected. This is the metastructure of smart cities. So as was previously discussed, digital twinning is one way of viewing the cyber-physical component of these solutions. Digital twins are computational models of real systems that incorporate real-time data from sensor networks and use high-fidelity computer models to predict the current or future performance of real-life systems. In order to predict the performance and degradation of our infrastructure, we combine fundamental material transport models, electrochemical corrosion models, and physical mechanics models into a multi-physics model. I get to go into a lot more detail than you did on digital. At the fundamental level, we model movement of ions through porous concrete materials using the Planck equation and validate these computational models against published scientific literature. I included these slides for you so that you could feel at home as a civil engineering professor. At the electrochemical scale, we model corrosion current density and potential along the reinforcing steel, in addition to modeling anode and cathode polarization curves to ultimately use Faraday's law to model corrosion and reinforcement as a function of time. Integrating these models together with a real infrastructure system, such as a reinforced concrete bridge, we can start to build our digital twin. We start with building information models, say a bridge column with a reinforcing cage. We can automatically port those into multi-physics modeling software and then port them into high-fidelity multi-physics models when combined with appropriate sensing and environmental data. So then we can start to understand the movement of all corrosive ions, gases, and corrosive ions and gases into the reinforced concrete structure, along with understanding the impact that they have over time. This type of predictive modeling is particularly interesting for understanding our new infrastructure systems that are exposed to yet unforeseen levels of atmospheric CO2 and ocean pH as a result of climate change. In the face of global climate change, all of our historical models for infrastructure costs and performance are in question. Let me repeat that. Everything we know about the cost of maintaining our reinforced concrete in traditional systems is now in question because the fundamental assumptions of temperature, humidity, pH are no longer valid over the next 50 to 100 years. Using these models, we can predict the occurrence and propagation of corrosion and deterioration of infrastructure and the formation of damage in the future that will require costly repairs. Running these simulations thousands or millions of times to account for uncertainty, we can build probabilistic risk-based cost or impact forecasts for our major infrastructure. We can predict the future. We can predict out in the future what the probability of repairs will be, along with the associated emissions. Moreover, we can start to design sound engineering fixes years, if not decades in advance, continuously update our models with sensor data, and leverage AI algorithms for management optimization. Connecting with existing frameworks of pay-for-success infrastructure bonds, digital twins of our major infrastructure can be used to forecast the reduction of future costs and environmental impacts and validate the efficacy through continuous sensing. Integrating existing reinforced concrete infrastructure technologies with newly developed computational modeling and financing schemes brings into reality our envisioned metastructure. But such opportunities are not limited to this example. A number of cost and revenue sharing approaches that are proposed for smart urban systems that include parking, traffic management, waste management, safety and security, and a number of other things discussed previously. Much like the digital twin example, all of them combine new, multimodal, sensor data collection points, Internet of Things, with domain-specific performance models. And this is important. We combine the Internet of Things with domain expertise to achieve higher levels of service and increase quality of life. This is not simply about electrical engineering. The combination of all these new tools is once again the urban metastructure. So in closing, I briefly want to talk about the Stanford Sphinx project. The Sphinx project, or Smart Financing for Smart Cities project, is not another technology demonstration. We know that future smart cities will be amazing, but will not be cheap to build or maintain. Unfortunately, many municipalities around the world do not have adequate funds to invest in these technologies or systems. The Sphinx project looks to unlock an expected $70 trillion in long-term investment capital worldwide that is currently underdeployed. We look to achieve this by developing models and teaching others how to understand, measure, and evaluate the financial risk and opportunities of smart city technologies, with a unique focus on the nexus between cyber-physical and financial models. We'll also investigate new urban data streams for potential revenue generation while looking to understand new models for smart and sustainable governance and finance. So in conclusion, future smart cities will be a complex nexus of infrastructure systems that include physical, cyber, social, financial, health, and many other types of infrastructure. The linking of these various systems together in new and innovative ways is the emerging urban metastructure. And we think this metastructure will be key to solving the urban wealth quality of life challenge. It can be used to open up new sources of funding and financing that we need to pay for smart cities in the future. Finally, next generation credit risk models that leverage the capability of smart cities and the urban metastructure, such as those that we're developing in the Sphinx project, will be critical to attracting the financing necessary to build smart cities in the future in which we all dream to live. I have to acknowledge many colleagues and graduate students who helped create these ideas and the funding sources that allow me to explore these interesting topics. Thank you.